Hi guys, thanks for enrolling in the course for the introduction of mud crab vertical farming. In the previous episode, we have talked about the theory behind biofiltration and the different nitrification rate between saltwater and freshwater and how to calculate total ammonia nitrogen. In this lecture, we will show you the different nitrification rates of the trickling filter, fluidized bed, and the moving bed bioreactor. This will help you size your biofiltration plant in the future. There are often very different types of biological filters. They can be in a form of trickling bed, which is commonly found in wastewater industries due to their huge size. And secondly, we have what we call fluidized bed that is commonly used in a cold water freshwater application. And lastly, we have the moving bed reactor, which is commonly used in the saltwater application. Firstly, let us talk about trickling filter. So trickling filters are known to be very reliable and they're known to be very big. So a good place to spot a trickling filter is probably at your municipal wastewater plant, in which they are probably processing from a paper mill or a small factory that has a runoff of wastewater. They're usually situated behind the factory with a 2 to 3 story high structure in which it only contains rocks inside and waters are trickled over the rocks. Trickling filter is easy to control the oxygen and is also easily control the CO2 due to its water wet surface. So how does a trickling filter work? Essentially, you just have water that is pumped up to the top of the tank and water is allowed to trickle over the rocks and it goes out at the end of the reactor. Now, as you can see, a simple way to build a trickling filter is simply just use an aquarium filled with rocks and where you pass the water throughout these rocks and the water will go through all the seams of the rocks, and this is where the beneficial bacteria will go on to uptake your ammonia along with oxygen to convert into NO2, and the other bacteria will convert NO2 to NO3. So what are the typical nitrification rates for this trickling filter? A good way is to estimate your total ammonia nitrogen given the formula earlier. I know that some formulas might be quite daunting to some of us. Therefore, we have benchmarked the performance for each cubic meter of media. As you can see, for every cubic meter of trickling filter that you use, which can be made out of simply rocks or pebbles, the nitrification rate can process up to 3 kilos of feed every day. So, the media cost is not that expensive as well because they are just rocks. Assuming that you have to feed a crab 3 kilos every day, you will then have to provide 1 cubic meter of this sand filter media. Or in other words, if you have to feed 9 kilos of feed every day, you will require 3 cubic meters of media. So this is how you calculate how much media do you need. Unfortunately, trickling filters, although they are very cheap, then they tend to be not very reliable. The reason is being so. As water flows through the seams through the rocks, what often happens is you might have algae or some sort of bacteria that forms a biofilm, and it tends to clog up the surface area available to treat the liquid. So you will find out after running your plant to 6 to 1 year, most of the seams have actually clogged up, resulting that you either have to clean out the rocks or just replace the media. So usually what do people do in this case? People tend to oversize 3 to 5 times bigger in terms of capacity and allow for the clogging to occur. So in this case, which is a wastewater trickling plant, what happened is you might have need 20% of your capacity, but you oversize them 3 to 5 times so to account for this clogging factor. Secondly, we come on to the fluidized bed reactor. They are very efficient and they are very compact, and they are also very cost competitive in terms of removing ammonia, NO2 to NO3. However, they are really only suitable for cold water applications. Why cold water? Because essentially, we have talked about ammonia being processed to NO2 and NO3. This process requires oxygen. And in cold water, the availability of oxygen is higher. I've also included this link to help you design and operate any fluidized bed reactor. So how does a fluidized bed reactor look like? For those who are familiar with aquariums, this is how a fluidized bed looks like. It basically is just a small reactor in which it has a lot of fine sands that is packed into this reactor. And using a small current, the sand is continuously moved up and down the column. So why do they move the sand up and down the column? It is because oxygen availability tends to decrease with increasing water depth. So as the deeper you go into the media, what you get is a lower oxygen. And we have discussed earlier that for the bacteria to consume ammonia to NO2 to NO3, you would require oxygen. So without the movement, which we call fluidizing the media, the bacteria that are situated at the bottom would not be able to perform nitrification that converts ammonia to NO2 to NO3. The bacteria at the bottom will move up to the surface, providing it with the additional oxygen. So this is also another clip of how a fluidized bed reactor actually looks like. One of the reasons why a fluidized bed has gained popularity in the recent years is because of a simple concept. The bacteria grows on the sand in an outward layer, so they form what we call a biofilm layer, which consists of a community of bacteria. Usually, the younger bacteria will reside at the core of the biofilm, leaving the older bacteria on the surface. However, the older bacteria are not as productive as the younger bacteria. Therefore, by fluidizing it, essentially you are removing some of the older bacteria by scrubbing them against each other and only keeping the productive bacteria. So now let's take a look at the nitrification rate of this fluidized bed reactor. Again, you can do it based on total ammonia nitrogen, or we can use our rule of thumb. For every cubic meter of media, you can process up to 30 kilos of feed a day. As you can see, by simply fluidizing the bed and also incorporating a smaller media, you can increase the nitrification rate by 10 times, and the media cost is relatively cheap. Therefore, fluidized bed reactor is much more efficient as compared to the trickling filter. However, it is only readily used in the cold water and freshwater industry. The third is what we call the moving bed reactor. The moving bed reactor has been the backbone of warm water, salt water rust biofiltration. This media is not made up of sand or stones. They are made from plastics. As you can see, this is the moving bed reactor for a tilapia farm in the US, and this media, which we have over here, is a media that we have been using in our crab farm. You can see it is just simply a plastics with a lot of surface area built into, leaving the bacteria to stay inside or one of these fins. And this is a commercially available product called K1, cold rest media. So this is how a moving bed reactor actually looks like. So this is a similar plant from the tilapia farm. As you can see, it's just being air pumps and the result, and from the effluent from the drum filter. It is also commonly used in aquariums for hobbies. And this is how the medias are being agitated in a reactor. So similarly, you have bacteria that are growing onto this media that have the opportunity to not only stay at the bottom, but go up to areas with high oxygen content. So as you can see, that you only require a small air pump to rotate this moving bed reactor. So what are the nitrification rates of this moving bed reactor? Every cubic meter of media, you can process up to 6 to 12 kilos. Why 6 to 12? 6 is when you're applying it in salt water, and 12 when you're applying it in fresh water. As you can see, the media cost is relatively expensive, and it is much more expensive than sand or pebbles. However, they provide very reliable nitrification. So assuming that if I have to feed 2 kilos of feed every day, how much media do I need? The answer is you only need 0.3 to 0.4 meter cube of media. If I have to feed 18 kilos of feed on a daily basis, I will need 3 cubic meter of moving bed reactor. In our farm, we are using the moving bed reactor, and it has shown to be very reliable in controlling the ammonia into NO2 to NO3. On a daily basis, we are feeding about 4 to 5 kilos of feed every day, and we have about 1 cubic meter of this media in our system. We are able to control the ammonia to 0 to 0.25 ppm on a daily basis while feeding at this high rate. Biological filtration is often the limiting factor in any RAS systems. Increase your feeding rate while maintaining the same water quality. It is important that you have sufficient media to ensure that your nitrification is happening properly. That's all for this lecture. In the next lecture, we will talk about disinfection technologies, mainly UV, ozonation, and biosecurity to ensure that diseases stay away from your aquaculture system.